In this video, I want to take a look at using power series again, but using them in a place where you don't have another way of solving the differential equation. And I want to take a look at one other variation that you might encounter. So here we go. Here's problem number 4 out of the homework set. Y double prime minus xy prime minus y equals 0, centered at x0 equals 0. What I notice here is that this is not constant coefficients because of that x right there. So we can't do this with just assuming y equals e to the r x. Go from there because that x is going to screw things up. So let's try it with a power series. So since I'm centering at x equals 0, just like I've done on the other two examples I've shown in the previous videos, the power series just looks like this, the derivative and the second derivative. One of the things that's kind of nice about centering at x equals 0 here is that this needs to be multiplied by x. And it's really easy to multiply this power series by x because it's already in powers of x, right? So when I take these and plug them into the differential equation, here's the second derivative minus x times the first derivative minus the function equals 0, that this x just distributes in really nicely, and the x times x to the n minus 1 is just going to be x to the n. It bumps the power back up to n. So that's what we do here. Actually, I brought the minus sign in as well. I brought that minus sign in as well. I find it easier to bring the minus signs in so that I don't lose track of them. Anyway, next thing I need to do, so I brought that x in. I need to re-index here, or I already did. Okay, so this here with the n minus 2, I had to change it to an n. So everything's being bumped up by 2 here. So the a sub n is a sub n plus 2, the n minus 1 is an n plus 1, the n is an n plus 2. And as we've done before, this is actually n. It doesn't need to be n equals 0 to infinity. It's actually n equals 2 to infinity, because n equals 0 would give me a 0, and when n equals 1, it gives me a 0. So this is a 2 here, and so the index is dropping down to 0. I double-checked myself. With this as a 2, the first thing I would get here is an x to the 0, right? So same thing here. This needs to be an x to the 0, so that comes down to a 0. Now, I have the same starting and ending points on my sums. They're all in powers of x to the n, so I can combine them into a single sum here with this coefficient minus that coefficient minus that coefficient, and we've got this, which the n minus this and that get together to create that. And then the only way that this power series is going to equal the constant 0 is if every one of these coefficients is equal to 0. So we set that equal to 0, and personally I like it better rather than n plus 2 and n. I'd rather have it as n and n minus 2, because I'm going to solve for the bigger one, a sub whatever the bigger subscript is, and I just find it convenient to have it be n. So I'm just going to re-index again and change drop everything down by 2 on the index. So I get a n equals a, what happens here? Yes, when you move this stuff over to the other side and divide by the n minus 1, the n minus 1's cancel out. So this is just a sub n minus 2 divided by n. And here we go. Yeah, so a0 and a1 would be determined by the initial conditions. Then a2 would follow this rule, a0 over 2. a3 would be a1 over 3. a4 would be a2 over 4, but I already know what a2 is. It's a0 over 2. And so I get that a4 is a0 over 4 times 2. And likewise, a5 would be a3 over 5, but I know what a3 is already, and I plug that in. And I know then a6 would be a4 over 6. And I'm going kind of fast here because it's just simple algebra at this point. You just got to be careful not to make little mistakes. But anyway, I can kind of see a pattern here that the evens, so a sub n if n is even, would be a0 over n times n minus 2 times n minus 4 times all the way down to 2. And likewise, with the odds, you'd have, if n is odd, then I'd have an a1 over n minus n times n minus 2 times n minus 4, and so on, down to 3, or down to 1, I suppose, but multiplying by 1 is kind of well, it doesn't do much. Anyway, plugging everything in here, remember y was being written as a power series, so a0 plus a1x plus a2x squared, but a2 was this, and a3x cubed, where a3 is a1 over 3, and a4x to the 4 plus a5x to the 5, and so on. I then can take all the stuff with the x-zeros, sorry, with the a-zeros. There's a 1, there's an x squared over 2, there's an x to the 4 over 4 times 2, there would be this x to the 6 over that thing, and so on. And likewise, look at the a1s. Okay. The purpose that I wanted on this problem, the thing I wanted to show you on this problem, is that multiplying by x, right? That when you're multiplying that y prime by x, it's really nice because it just bumps the index. It just bumps the exponent back up, right? Where that was an x to the n minus 1, when you multiply by x, it goes to an x to the n. Okay. Now, this was not actually problem 4, because problem 4 says do it centered at x equals 1. So my power series looks like this. It's an an x minus 1 to the n. Okay, now I haven't done an example like this, which is one of the reasons why I want to put this in this video. So taking the derivative, n, right, the n comes out in front, an x to the n minus 1. There is a chain rule that says times the derivative of the inside, but the inside has a derivative equal to 1, so the chain rule doesn't really come into play here, and then take the derivative again for the second derivative. The thing is, now this multiplying by x is really no fun, because it doesn't, I mean, it does just distribute it in here, but then you'd have an x times x minus 1 to the n minus 1, and it doesn't just bump the exponent back up again. So what I'd rather do is I'd rather multiply by x minus 1, because my power series is in terms of x minus 1. So what I'm going to do is I'm going to change that differential equation. Rather than an x there, I'm going to change it to an x minus 1. You say, but Will, you can't just do that. I'm going to say, I can do anything I want, as long as I do it right. And the as long as I do it right part is compensate, right? That is, with an x minus 1 here, instead of just an x, if I distribute that, the negative y prime in, I'd have minus xy prime, which is what I started with, but I'd have an extra plus y prime. So I need to compensate by subtracting another y prime, right? If you distribute this out and collect some like terms here, you'd have a minus xy prime, plus y prime, minus y prime. Those would disappear and you'd be right back to where you started from. Okay. So I changed it into what I wanted, and then I compensated to make sure it's equal to the same thing. But you see now, I'm multiplying by x minus 1, which is going to be easy to do. And then I just got that y prime by itself, which is already in terms of x minus 1s, and so we're good. So now plug in everything in, and I'm going to move this a little bit to see if I can get everything on the screen here. Yeah, there we go. So I've got the second derivative, minus x minus 1 times the first derivative, minus the first derivative again, minus the function, and that is supposed to equal 0, which is not even on the screen yet. In fact, it's not even on the web page screen. So here we go. There is an equal 0 off to the right here. Let's continue on down. I'm bringing this inside, which bumps that back up to an n. Bringing that minus inside, bringing that minus inside. You can just begin to see the equal 0 here before it disappears off the side of the page. Anyway, and I have not re-indexed yet, but at least I noticed that I don't need a 0 here. I can change that to a 2. Now I'm going to re-index this one, so it's in powers of n. This one already is in powers of n. Actually, up here, I didn't mention it, but I also changed that from a 0 to a 1 because the n equals 0 doesn't matter because it's a 0. So start at 1. And then when I re-index, bumping that up to an n, I've got to knock this down to a 0, which it isn't. And let me change that real quick. All right, now I changed it, but I also changed the font size so that we can see some more stuff. So this one was re-indexed. This one was left alone. This one was re-indexed. And this one was left alone, and it is equal to 0. So now I have everything in terms of x minus 1 to the n, and starting at n equals 0. So I can combine them all into one. It looks like this. And now the only way that's going to add up to 0 is if each of the coefficients is equal to 0. So all of this stuff has to equal 0. And then what I want to do is I want to solve for the a sub biggest thing. So I got n plus 2, I got n and n plus 1 and n. So I'm going for the a sub n plus 2. So this stuff gets moved over to the other side and then divide by those things. And what happens here, actually let's make the font a little bigger again. Combining some like terms, there happens to be the ANs, there's n of them and one more, so there's n plus 1 of them, then there's a factor of n plus 1 that cancels out top and bottom, leaving just an plus a n plus 1 all over n plus 2. Again, I like this not with an n plus 2 over here, but rather with an n. So I'm re-indexing, dropping all the indexes by 2 here. So every place I see an n plus 2, I'm replacing it by an n, and so on. So A0 and A1 will depend on the initial conditions. A2 then would be A0 plus A1. This is with n equals 2. We plug a 2 in for the n's there, right? A0 plus A1 over 2. A3 would be A1 plus A2 over 3. But A2 we just calculated was that. Multiplying top and bottom by 2, I get that, yeah, A0 plus 3A1, because there'd be 2 there plus 1 more here. And the denominator becomes a 3 factorial. Then A4, with n equals 4, I've got A2 plus A3 over 4. A2 we calculated up here as this. A3 we calculated there as that. Multiplying top and bottom by 3 factorial. That would be 3 times this stuff plus that stuff. So divided by 4 times 3 factorial is just 4 factorial. And I get a total of 4 A0s plus 6 A1s over 4 factorial. And then likewise A5 would be A3 plus A4 over 5. I just calculated A3 and A4, multiply top and bottom by 4 factorial to get this and that, and A6 in a similar way. Just keep going. Honestly, at this point, I don't really see a pattern. I mean, I could, maybe I could work a little harder and find it, but I don't think I need to. Actually, when I read the directions of what they ask you for this problem in the book, it says find the first 4 terms of each of the 2 solutions. And so I'm going to just plug everything in here. Y equals, I got the font wrong right there. Y equals A0 plus A1 x minus 1 plus A2, which is this, x minus 1 squared, plus A3, which is that, x minus 1 cubed, plus A4, x minus 1 to the 4 power, and so on, right? Now I'm going to move things around, say, what's times A0? Well, there's a 1 times A0. There's a half times that times A0, and there's a denominator of 3, which should be a denominator of 2. That looks a little better, also a little smaller, so we can see some more stuff. We've got A0s, right, that one. There's the half times x minus 1 squared. There's an A0 over 3 factorial times that. And there's a 4A0 over 4 factorial times that. and so on, plus dot dot dot. The A1s, there's an x minus 1. There's a half x minus 1 squared. There's a 3 over 3 factorial x minus 1 cubed. There's a 6 over 4 factorial x minus 1 to the fourth, and so on, right? So I got the first 4 terms in each of those series for the 2 independent solutions to that homogeneous equation. Now it's interesting, I've always wondered, is this 4 terms or is it 5 terms? Because I count 1, 2, 3, 4, but technically there's a linear term in there whose coefficient is 0. And it's like, so maybe I've got 5 terms here, I don't know. I'm going to count it as 4 for the sake of, I've got 4 things that I can see, right? So there you go. You can be creative as long as you do it legally. So have fun.